So today we're in lecture 3 out of 4 about game theory, and we're going to keep delving into different kinds of game models, and again devote some effort to talking about applications in AI. Specifically today we'll be talking about the application of game theory to game playing, which seems like not a very surprising application, but nevertheless there are very interesting aspects to it. So let's actually start with a very basic model. This is the model that people often start talking about game theory in general with. I actually chose to talk about it a bit later, but as you'll see, it's sort of something very simple, and we'll actually come back to this model in the next lecture. So the model is zero-sum games, and the representation is sort of very similar to normal form games. So this is a special case of normal form games. The difference is that, as the name implies, we're assuming that the values, the payoffs to both players, sum up to 0. Hence the name zero sum. So here's, and the way we represent it is we just show one number in every entry, and that number is going to be the payoff to player 1, to the row player. Okay, and then we assume that the payoff to player 2, to the column player, is negative, whatever we're showing for the row player. So here's a simple example. It's a game of kicking a ball in soccer. So there's a kicker and a goalie. The row player is the kicker. The column player is the goalie. And then if the row player, if the kicker kicks left and the goalie jumps left, then he stops the ball. And then player 1 gets -1. Player 2, the goalie, gets 1. So player 1 loses, player 2 wins. If the kicker kicks left and the goalie jumps right, then the ball goes in, and then the kicker wins, the goalie loses, and so on. So that's a really simple example. Now, in the context of zero-sum games, the kind of solution people often talk about, or always talk about, is what's called maximum strategies. So the idea is we're going to look, if we take the point of view of player 1, we want to maximize the worst case expected payoff over what player 2 is doing. And if we are player 2, we want to minimize the payoff, because remember, this is the payoff to player 1, and our payoff is sort of the opposite. So if you think about a penalty shot game, it's very intuitive that the optimal strategy for both players is playing 1/2, 1/2. Because if, for example, you decide to give higher weight to left than right, then the goalie will jump left, and then will be able to exploit you. So it's very intuitive. You want to play 1/2, 1/2. That's the maximum strategy for player 1, the minimax strategy for player 2. So let's look at a slightly different game that won't be symmetric. Will make things slightly more interesting. So I'm just going to replace this payoff with -1/2 instead of -1 like before. And let's compute the maximum strategy for player 1 in this game. So we're just saying, well, player 1 is going to play up with probability P and down with probability 1 minus P. Now, what we want to do is look at the two possible responses for player 2. So if player 2 jumps left, player 1 will get P times -1/2 plus 1 minus P times 1, which gives us this utility. If player 2 responds by jumping right, then player 1 will get, so we're here, so we'll get P times 1 plus 1 minus T times -1, which gives you this. Right? And what you want to do is maximize the minimum of these two things over P. So these are two linear functions. Two linear functions. So the thing that will maximize their minimum is the intersection point. So to find it, just say 1 minus 3/2 P equals 2P minus 1. You solve it, and you get your optimal strategy. Okay? Is this clear? Okay. Just want to make sure everybody is okay with this. I went over this very fast, but it seems quite intuitive. Yeah.
Why we maximize the minimum of 2?
Right, because from the point of view of player 1, the payoffs that we're seeing is the payoff to player 1. So we're sort of assuming that player 2 is responding in a way that's worst for us, because he's getting the opposite payoff. Right? So we're saying, we want to guarantee to ourselves as much as possible. Okay, and this notion of being able to guarantee to ourselves a value will be important in 2 slides. Okay, any other questions about this thing that we went quickly over? Okay, so I want to claim, one very nice thing about zero-sum games is that unlike general sum games, when we talked about Nash equilibrium, and like correlated equilibria, computing these maximum strategies can be done in polynomial time through a linear program. Let's see what it looks like. It has the form that we talked about when we talked about integer programming. So we want to do max-min. But remember, when we talked about it at the time in the context of the max-min share guarantee in fair division, we said max-min, even though it doesn't seem like a linear function, it is something that you can write linearly. And we can do the same thing here. So what we'll do is W will be the payoff to player 1. And we want to maximize this W. But W is defined by like our minimum payoff over any response of player 2, any strategy player 2 can play. So what we're saying is our variables are going to be the probability that we play each strategy. And we're saying for every S2, for every response of the other player, our expected payoff is at least W. Okay? And then because we are trying to maximize W will see, so we're trying to push W as up as possible, but it will be constrained by the minimum of all of these, which gives us this max-min objective that we want. Okay, so this says sort of maximize the minimum, choose the probability distribution, maximizing the minimum payoff for any action of player 2, and this has to be a probability distribution, and the probabilities are at least 0. Right, so this is pretty cool. When we're in this more restricted setting, which is very natural, then we can actually compute optimal strategies, or these max-min strategies, in polynomial time. Okay, so here's a beautiful theorem about zero-sum games. So these were actually explored or understood well before general sum games. Nash's theorem is 1950. This is a 1928 theorem by von Neumann, which says that every 2-player zero-sum game has a unique value V, which is sort of the value that can be guaranteed. So player 1, the role player, who's trying to maximize this value, always has a randomized strategy that guarantees him at least V. And player 2, the column player, always has a randomized strategy that guarantees that the expected payoff to player 1 is at most V. He's trying to minimize this payoff. Okay, and then V is called the value of the game. So this is a pretty striking thing. For those of you who have seen LP duality, you can sort of derive it from the fact that this is an LP and using duality. We haven't studied LP duality. We'll actually spend all of the next lecture proving this theorem through a pretty convoluted proof. So I'm going to prove it through no-regret learning, which I think is just like a really cool thing to do, because this is a really cool area in learning theory. So it will show you another, we talked about pack learning, so this will show you another area of learning theory that has very interesting connections to game theory. So this is, I think will nicely illustrate one of the basic connections, and then we can maybe build on it in the homework. Okay, so we'll do the proof of this, a pretty complicated proof, because we'll have to prove some theorems in no-regret learning in order to prove this one. So hopefully it should be fun for those of you who like theory. Yeah.
So V can be negative here, right?
V can be negative, yeah. Yeah, so for example, if all of the payoffs in the game are -5, then V will be -5. Anything you play will give you -5. Okay, so here's a question for you. So the question is, how many Nash equilibrium payoffs do zero-sum games have? And the reason I'm asking this way is, for example, it's very obvious you can have many Nash equilibria, like in this game I just described, where all of the payoffs are constant. Let's say every payoff is -5. Obviously, every pair of strategies you would play would be a Nash equilibrium, but they would all have the same payoff. So the question is, how many Nash equilibrium payoffs do zero-sum games have? At most one, at least one, or exactly one? So of course, if you say at most one, then exactly one is also true, but choose like the most accurate answer. Okay, great. We have a majority for the right answer, which is exactly one. So would anybody like to say why it's exactly one? So this, we can deduce this from the theorem that we just stated. Hitesh?
It will be exactly V, because if it is not V, suppose it is more than V, then the second player, since he can guarantee at most V, he can change the strategy and reduce the value.
Excellent.
So, and if it was less than V, then player 1 could change the strategy.
Excellent.
So the Nash equilibrium has to have.
Perfect. Right. So Ritesh is saying, the only payoff in Nash equilibrium will be V, right? Because an argument is if it's something else, then one of the players can deviate. Each player can guarantee to himself a value that is V. So if it's larger than V, player 2 will deviate and get less. If it's less than V, player 1 will deviate and get at least his guaranteed value, which is V. Right. So the point is, in this setting, Nash equilibrium actually coincides with these max and min strategies. Okay, so it's really like a simpler setting. Okay, good. So now that we have that in mind, keep that in mind. We're going to talk about extensive form games and then talk about zero-sum extensive form games. So extensive form games, this is another very useful model in game theory. So the difference here, when we talked about normal form games, we said that the two players move simultaneously. Here, the moves are going to be sequential, not simultaneous. So the way we illustrate this is the game is defined by a tree, where every node is labeled by the name of the player who makes a move in that node. And then the payoffs are at the leaves. So like before, for each payoff, so if player 1 chose to go left and player 2 then chose to go right, the payoff to player 1 would be 5, and the payoff to player 2 would be 3, like before. Okay, so, I guess one question you could ask is, how is this different from a normal form game? Okay, so it seems sequential, but one thing that I want to note is you can actually represent this as a normal form game. And the way to do it is we will define a strategy by what you do in every possible node in the tree. So in this game, player 1 has only one node, so you can only take left or right. But player 2 has a choice in this node and a choice in this node. So we can define a strategy by two actions: what he does in this node, left or right, and what he does in this node, left or right. So now we get 4 possible strategies for player 2. Right, so for example, let's just check what's going on. So if player 1 plays left and player 2 plays right and left, then that means player 2 went here. Then player 2 chose right, and we get the payoffs 5-3. Okay? So what's relevant, like if player 1 chose left, what's relevant is only this part of the strategy of player 2, not the other one. Or if player 1 goes right and player 2 plays left-right, then we go right and end up with 3-2. Okay, so again, every time, like when we look at the strategy of player 2, the only thing, the part of it that's relevant is the one that's defined by what player 1 chose to do. Okay, okay, so we can do that. One issue is that the number of strategies here becomes exponential in the representation of the game. But I actually want to tell you about, I think, a more interesting issue, or in more detail, which is the following issue. So let's look at this game. This is like a Cold War-inspired game. And the US, so we're thinking of two players, the US and the Soviet Union. The US, so there's some, so I think of like the missile crisis, the Cuban Missile Crisis. So the Russians were moving missiles into, or the Soviets were moving missiles into Cuba. And the US had two possible actions, either to ignore what's going on or to respond by putting a blockade. And then the Soviet Union had two possible responses if the US chooses to respond, either to compromise, which is what happened, or start a nuclear war. So what we're saying here is if the US ignores, then the Soviet Union, player 2, is getting a slightly higher payoff. If the US responds and then the Soviet Union compromises, then the US is getting a slightly higher payoff. But if there's nuclear war, the world is destroyed, and that's like really horrible payoff to everybody. So, so like before, we can represent this game, but here, I mean, there's just one action for each player, right? So it's just a 2x2 game, and we can look at the different payoffs, just map them into the game. However, now think about this. Think about this pair of strategies. So the US ignores, and you still have to define for the Soviet Union what it would do if you reach this node. Right? So to talk about equilibria, we have to say, okay, if one player changes, now we can reach new nodes. So what would the other player do? So we still have to talk about what the other player would do. And we're saying, well, if we did reach this node, then the Soviet Union would start a nuclear war. So if the US did choose to respond, the Soviet Union would start a nuclear war. So this is a Nash equilibrium in this game, fine. But now let's think about like the sequential game interpretation of this. Because the players aren't actually moving simultaneously. So, what's happening here is from the point of view of the US, it's thinking, oh, I don't want to deviate. Because if I deviated to respond, then I know the Soviet Union would start a nuclear war, and therefore I'm better off sticking with ignoring. However, the issue is that this, the Soviet Union saying, I'm going to play, like if we reach this node, I'm going to play this. This is not what's called a credible threat, right? Because if the US indeed chose to play this way, so now the Soviet Union now faces two choices, either to compromise and then get a payoff of 1, or to start a nuclear war and get a payoff of -1 billion. So it's not credible for the Soviet Union to say, okay, if you put me in this situation, I'm going to go crazy and start a nuclear war instead of compromising and getting slightly smaller payoff. Okay? So, and then the US can sort of reason about this and say, okay, there's no way the Soviet Union would, and that's basically what happened. There was actually a lot of this type of reasoning in the 60s, when this was going on. So, so then the US can say, well, there's no way that the Soviet Union would actually respond that way. That would be irrational, and therefore we should respond right now, and we can assume that the Soviet Union will compromise and not start a nuclear war. So this is, so you can map this to a normal form game, and you can talk about the Nash equilibrium, but this, when you interpreted it in the sequential story, this Nash equilibrium doesn't really make sense. So that's why people have introduced a stronger notion of equilibrium that is defined for extensive form games. And this is this notion of subgame perfect equilibrium. So the idea is that now we can think of every subtree as a subgame. So for example, in this game, this is kind of a degenerate game, but maybe we have a better game, yeah. So like in this game, you can say, okay, this is the whole game. But you can also look at this subtree. This defines its own game, a game where player 2 plays first, and then player 1 might play if player 2 goes left. Right? That's also a game. You can sort of cut the tree at that point and say this is a game in itself. And this is another game which player 1 plays with himself. So he is the only one who takes an action, and he can go left or right. So the point is every subtree is a game. And the subgame perfect equilibrium is one where this set of strategies is a Nash equilibrium in every subgame. So what we had before, when we said the US ignores and the USSR starts a nuclear war, this is not a subgame perfect equilibrium, because if you look at the subgame that is just defined by this node, then it's not a Nash equilibrium for the USSR to start a nuclear war. Like if it's the only action, we start from that point, it would want to compromise. Okay, so this rules out this kind of non-credible threat that we had before. Okay, so one really nice thing about this is that a player, when you take this type of reasoning, a player can actually improve his equilibrium payoff in a subgame perfect Nash equilibrium by eliminating strategies. So in this game, if we eliminated the compromise strategy for the Soviet Union, then it would actually be, then the US would actually want to ignore rather than respond and then start a nuclear war, right? So, if we knew that basically if we go here, we definitely get the minus billion minus a billion, then the only thing for the US to do in an equilibrium would be to go right and ignore. So this is kind of ironic, right? We remove some of the options of player 2, and we can actually improve their payoff in an equilibrium. So this is something that was captured really nicely. I mean, there's been a lot of Cold War thinking around these issues, and there was, it's been captured in this pretty crazy Peter Sellers movie, Dr. Strangelove. So there's one scene that I want to show you where Dr. Strangelove explains this type of reasoning. I mean, the idea is that the Soviet Union did build this doomsday machine that basically removes the option of compromising. So if they're attacked, if there's any aggression, then it automatically starts a nuclear war. So I'll let Dr. Strangelove explain the rationale.
After the authority granted me as Director of Weapons Research and Development, I commissioned last year a study of this project by the Bland Corporation. Based on the findings of the report, my conclusion was that this idea was not a practical deterrent for reasons which at this moment must be all too obvious.
Then you mean it is possible for them to have built such a thing?
Mr. President, the technology required is easily within the means of even the smallest nuclear power. It requires only the will to do so.
But how is it possible for this thing to be triggered automatically and at the same time impossible to untrigger?
Mr. President, it is not only possible, it is essential. That is the whole idea of this machine, Deterrence is the art of producing in the mind of the enemy the fear to attack. And so, because of the automated and irrevocable decision-making process which rules out human meddling, the doomsday machine is terrifying. It's simple to understand, and completely credible and convincing.
Gee, I wish we had one of them doomsday machines, Nancy.
But this is fantastic, Strangelove. How can it be triggered automatically?
And it's remarkably simple to do that. When you merely wish to bury bombs, there's no limit to the size. After that, they are connected to a gigantic complex of computers. Now then, a specific and clearly defined set of circumstances under which the bombs are to be exploded is programmed into a deep memory bank. A single row of chips can store all the information.
What kind of name is that anyhow? Proud name?
In the 25
It changed it when he became a citizen. It used to be perfectly legal.
A crop line in the name, wasn't it?
Is that the whole point of the doomsday machine is lost. If you keep it a secret, why didn't you tell the world, eh?
Okay. So now the question is, how do we find this subgame perfect equilibria? And the thing is, it's actually really easy to do, and it's done by this method called backward induction, which is something, if you guys have seen things like alpha-beta pruning and so on, it's something you probably have seen as like the basics of these kind of algorithms. So the idea is very simple. What we do is we start from the leaves, and then we look at the player whose turn it is to play. We take the best action for that player, and we replace the leaf with the payoffs that are obtained when the player plays that action. And then that becomes a new leaf, and we keep doing this until we reach the root, which would give us the payoffs for the game. So for example, let's look at the game we had before. So we first look at this leaf. Player 1 can choose to get either payoff 1 or get payoff 0. So we would go left and get payoff 1. So we can replace this leaf with the payoffs 1 and 0, which is what happened here. Now we look at this leaf. So player 2 can choose between 4 and 3. It would choose 4, of course, and then we can replace this by 2, 4. Now, in this leaf, player 2 chooses between 0 and 2, so it would choose 2, and we can get 3, 2 here. And now player 1 chooses between 2 and 3, so it will choose 3, and then the payoffs that we get at the root are 3 and 2. Okay? So this is the backward induction solution to this game. And now, we also keep track of what each player chose in every node, and that gives us the strategies that are in subgame perfect Nash equilibrium. So in the game that we just looked at, I just recorded what we chose to do in every node and marked it here. These are the subgame perfect Nash equilibrium strategies. So why is this a subgame perfect Nash equilibrium? I think the intuition, maybe we'll prove this formally in the homework, but the intuition is pretty clear. You basically do the best thing at every possible stage in the game. So assuming the other player does the best thing for him, then if you change, then you'll do something suboptimal for you, right? But notice that another thing you can pretty intuitively see, I think, is that every subgame perfect equilibrium is obtained by backward induction. And the reason is that at the leaves, if you're in subgame perfect equilibrium, you have to do what this thing is doing. But those become the new leaves. Right? So if you sort of do this by induction, it sort of forces you to take the backward induction action at every step. And that's why if you want a subgame perfect equilibrium, you'll have to end up with these kind of things. Yeah, Ankush?
What if you receive the same payoff along?
Right, so then you can choose either one, and all of these will be subgame perfect Nash equilibrium.
And can there be cycles in the graph?
No, so this is a game tree.
Okay.
Okay. So here's a question to you. It's just maybe something one might be confused about. I sort of framed it in a misleading way. So remember, when we talked about normal form games 2 lectures ago, we said, if you think about rock, paper, scissors, it doesn't, we talked about pure Nash equilibria. We said, oh, now we're in trouble because this game doesn't have a pure Nash equilibrium, right? Because if you chose any pure strategy, the other player could deviate and take something that defeats you. And then we need to resort to mixed strategies. And we said, according to Nash's theorem, there's always a mixed Nash equilibrium. Now, what we just said here is that we didn't talk about mixed strategies at all. I told you can just solve the game by backward induction. You get a pure subgame perfect equilibrium, which in particular is a Nash equilibrium. And moreover, we said before that extensive form games can be represented as normal form games. So what's going on? Like why? It's not even a question. Let me answer my own question, just in case you guys were wondering. So I think one way to think about this is if let's think about rock paper scissors, which is the game that caused us problems before. So there we were saying, well, the problem is that if the two players are playing together, one player and they sort of see what each player sees what the other is doing. The player who is tied or losing could always deviate and get a winning strategy. But if we think of this as a sequential form game, so let's say player 1 first chooses rock, paper, or scissors, and then player 2 chooses. So the way the game would look like is player 2's strategies is defined by what player 1 is doing. Okay, so in the normal form game, we said the two things are independent. But now you have this tree where player 1, you would have like player 1 chooses between rock, paper, or scissors. And then, for each node, player 2 chooses between rock, paper, or scissors. But notice that we said a strategy for player 2 says what he does in each one of these situations. So, and the crucial point is the strategy of player 2 can depend on the strategy of player 1. So player 2 would basically say, oh, here, if player 1 played rock, then I want to play paper. And we get -1 here. If player 1 played paper, I want to play scissors, and we again get -1. And if he played scissors, I want to play rock, so I can always win. But here I'm allowing player 2 to choose a strategy in a way that depends on the strategy of player 1. Okay, so that's, it's still a normal form game. It's just like a different type of normal form game because here we would have 8 possible strategies for player 2 instead of just 2. So you can say, actually 27 strategies. Right, so he has 3 choices in each node. So you can say what he does in this node, what he does in this node, and what he does in this node. So for these, so it turns out, as we just showed, that for these specific types of normal form games, you always have a pure Nash equilibrium. Okay, so hopefully this this could have been more confusing than helpful, but hopefully it gave you some intuition regarding what's going on here.
Well, here player 2 always wins.
Yeah, I mean, yeah. So this is just like one sequential form interpretation of rock paper scissors. You're right that it's not
You
your.
added one more move and player 1 wins.
Sure, right. So it's not. I mean,
Third game.
it's not a fair game, and it's not the original game, right? Sure. So just to illustrate the fact that in a sequential game of the type we talked about, it's really a case where the strategies of one player can depend on the strategy chosen by the other player. Right?
Yes, so it's kind of saying that like these games cannot be represented in the normal form game.
They can. I mean, so some normal form games, of course, have pure Nash equilibria, and I think, I mean, it says they can. It's just, if you take an extensive form game, write it out as a normal form game like we did, it will be a normal form game. So what would happen here is you would have this this matrix with 3 actions for player 1, 27 actions for player 2, and then when player 2 chooses like the strategy with the good responses, this would be a Nash equilibrium. Right? Yeah, so basically like from player 1's viewpoint, whatever he does, he loses, so he can't deviate. And then for player 2, he always wins, he's happy. Okay, cool. So let me show you just one cool example. Remember that when we talked about Nash equilibria, we talked about that funny game where you choose a number between 2 and 100 and the game theorists do the wrong thing. So in game theory in general, people talk about many, many different solution concepts and different models. And one of the things that motivates talking about new solution concepts is examples where the old ones do badly. So here's an example where subgame perfect Nash equilibrium gives you the sort of a bad or unintuitive outcome in this game. So this is called the centipede game. And this is the game tree. Okay, so the root is here, and if you sort of turn it on its side, you'll see that this is a tree, of course. And okay, so let's solve this game tree by backward induction. So we start from the leaf. The only leaf here is the one level above the leaves. So the only node like that here is this one. So basically, player 2 faces the choice between getting a payoff of 6 or a payoff of 5. So of course, he would choose a payoff of 6. So then player 2 in this node chooses this strategy, going down. Now player 1 here chooses between getting a payoff of 5 or getting a payoff of 4. So if he goes right, we already know that player 2 will go down. So player 1 is choosing between 5 and 4. So he would choose 5 and go down. Now here, player 2 can either go right and get 5, or go down and get 3, or go down and get 4. So player 2 would choose to go down and get 4. Okay, and then if we continue doing this, so basically what happens is every player in each node chooses to go down instead of to the side, including in the first node. So the game would end after one move, and player 1 would just choose to get the payoff 1, giving the other player -1. But if the players were more generous and less rational, I guess what would happen is with like normal people is people would start, I mean, this has also been shown in experiments. People don't go down immediately. They start by going right, and at some point somebody sort of deviates and go down and finishes the game. And that is more likely to happen as you're reaching the end of the game. Right, so for example, for player 2, if player 1 was generous and we got all the way up here, it makes no sense for player 2 to go right instead of going down. And the problem is that when you apply this reasoning recursively, you end up in a situation like we did before, which gives really bad payoffs to both players. So it's again a situation where game theorists would probably end up with this like really bad payoff, but most normal people go right for a while and end up getting much higher payoffs than the game theorists. Okay, so this is on a high level, some of the basic theory behind extensive form games. Now I want to spend a few minutes talking about games, actual games and how computers have been able to play them. And then I'll focus a bit more on poker, and then we'll talk about some more technical challenges. So just on the story level, there's a theorem dating back to 1913 by Zermelo that says that in a game like checkers, either white can force a win. So we don't know which player has which one of the following options is true, but we know that one of them is true. So either one has a winning strategy, can force a win, or black has a winning strategy, or both sides have a strategy that can force a draw. So this is pretty remarkable because he was able to say that, it's this huge game tree. It's impossible to analyze exactly, it was done like a century later, but it's pretty ingenious that you can make such a claim even though the game tree is so complex. And the proof is incredibly simple. So I'll prove it to you. It's 2 words, backward induction. And the way to think about it is if you actually wrote out this huge game tree that corresponds to checkers, you basically have 3 possible things in the leaves. Either 1, -1, or -1, 1, or 0, 0 if there's a tie. Now, when you do backward induction, which ultimately tells you what you can force at the root, like which payoffs the players can guarantee to themselves, when you do backward induction, every time you take a pair of payoffs and you propagate them 1 level up. That means that the only possible pairs of values that can propagate are 1, -1, -1, 1, and 0, 0. So ultimately, like when you do backward induction, one of these 3 combinations will propagate to the root, and that will be the value that both players can force. Okay, so it's really, once you see this idea of backward induction, which Zermelo introduced, then this theorem is pretty obvious. But it actually says something very powerful with like this very, very simple tool. So, so we knew for a long time that one of these 3 options is true, but we didn't know which one of the 3 options is true. And then in 2007, I told you the story in the intro lecture. Jonathan Sheffer from the University of Alberta actually solved checkers. So it was a big engineering feat at the time, plus a lot of algorithms for making the game tree smaller, so pruning the game tree. It took 18 years of computation. Probably today it would be much, much faster. And the result was that it's a tie. So, it took a century to discover which of the 3 options is the truth, and that means like his program can always force a tie, but it sort of plays perfectly. So essentially, if you make any mistake, you will lose. But if you play perfectly as well, then then it's going to be a tie. And yeah.
So what do you mean by 18 years of computation?
So we started in '89.
Like the program was running for 18 years?
Yes.
Oh my God.
Yes. Yes. So yeah, and over time he added more hardware and so on. I heard him give a talk about it in 2008. His hardware became better over time, but yeah, he started like the actual computation in '89. So it's it's a pretty amazing feat. And yeah, one huge problem he had from an engineering viewpoint is just making sure that it doesn't have any errors in the computation, right? If he has over 18 years, like any bug, then that will ruin the whole thing and like destroy 18 years of work. So there was like a very big challenge from a systems viewpoint of just error correction and making sure, from a storage viewpoint, just making sure there are no errors whatsoever. Okay, yeah, and I told you briefly like that story that I won't repeat it, but there was this basically perfect human checkers player, Marion Tinsley, and part of the obsession was being able to like decisively beat that perfect player, or at least proving that he could have beaten him if that program had played against Marion Tinsley. Anyway, so checkers was solved, but checkers has 10 to the 20 nodes. Chess is a much bigger game with 10 to the 40, and Go has 10 to 170. So still, this was a big achievement, but it's still a relatively small game compared to these bigger challenges. So this is another point we talked about in the intro. I guess all of you know about it. In 2016, last year, I think it was like in May or June, AlphaGo beat Lis Sedol, who's one of the strongest players in the history of Go, some people say, in a 5-game match. And this was really, again, a huge achievement. Now, the thing to note here is this was not done by solving the game. It was done by things like deep learning. But this is again a game where we have a very good understanding. At this point, computers can beat top humans, but it's a different kind of thing. The game hasn't been solved. So here's actually a really nice XKCD comic from a few years ago. It's a bit out of date. But what he did here was arrange different games according to the state of the art in terms of how well computers perform against humans. So in the top category, it's games that are solved. So things like tic-tac-toe are pretty easy to solve. And then checkers are sort of more pushing the boundary on that side of this illustration. The other side is kind of amusing. So there are 4 games here. Snakes and Ladders, which is like a game of pure chance. So this side is like games where top computers may never outplay humans, right? So Snake and Ladder is like a game of pure chance. It doesn't really, or there's no real strategy here. 7 Minutes in Heaven. I guess in Israel we called it 5 Minutes in Heaven, but I guess you know the idea. But then the 2 other games I actually wasn't familiar with when I saw this comics at first. So it turns out that I looked up on Wikipedia. Mao is this game where the players are not told what the rules are. So basically, like you take actions, and every time you take an action that is illegal, you're told which action you took that was illegal, but you're not told which rule it broke. And then you have cards, you're supposed to shed cards, but you're never told what the rules are, and you're supposed to figure them out for yourself. So I think, if I understand correctly, as long as the rules are fixed, this seems to me actually a game that deep learning would tackle pretty well, or deep reinforcement learning would tackle pretty well. So I disagree on the placement of this game here. But Kelvin Ball is actually another game that I didn't hear of. So here the rules change every time. It's like a ball game, but it can be like anything basically, and you change the rules every time, and you can make new rules on the fly. So this, if you do change the game every time, this is something that computers will not do very well in. But then, other games that we're interested in, so we said checkers is over here. Chess, as we discussed in the intro lecture, in 97, Deep Blue beat Garry Kasparov. So this is a game where computers can beat top humans. What he actually says here is that 2005 is the last time a human beat a top computer. So at this point, humans just cannot beat computers in chess. Then Go, as we said, moved from this category to this category last year. And what I want to focus for the remainder of the lecture is poker, which as of the time of this comics was still in this category and also deserves to be moved 1 category up. Okay, so any questions so far? Okay. So in order to think about poker, we need to introduce a more advanced version of extensive form games of imperfect information. So we're going to have a few novel components here. The first is we're going to have chance nodes, which basically, some people also call them a move by nature. It's like there's some randomization going on. It's not that a player chooses a move. It's just some coin toss that happens at that node. And another very important notion that we'll introduce is an information set, which is a set of nodes that belong to the same player, such that the player can distinguish between which of these nodes the game is in. Okay? And the constraint is that the player will have to choose the same action. Like when we talk about a strategy, it's constrained to use the same action in every node in the information set because the player can't tell them apart. Okay, so that's the last point of a strategy must be identical for all nodes in an information set. So let's look at this game and illustrate these concepts. So the way this game works is we first have a chance node that flips a coin and gets, it's an unbiased coin, so get heads with probability 1/2, tails with probability 1/2. Then it's the turn of player 1. Player 1 can look at the coin, so he knows if he got heads or tails. Okay? So these 2 nodes are in 2 different information sets. Player 1 knows what the coin is, and then can choose to either fold or bet. Now this game is defined in a slightly weird way. So if he got tails and he folds, he gets a payoff of 5, which is the highest possible payoff in the game. If he got heads and he folds, then he gets a payoff of -5, which is the lowest possible payoff in the game. Now, if he bets, then we reach the turn of player 2. And the two nodes of player 2 are connected by this dashed line, which means they're in the same information set. And the idea is that player 2 doesn't know if player 1 has heads or tails. Okay, so basically, these two nodes, we got them by the two different coin flips, but player 2 doesn't know if we reach his turn from this node or this node. So these two are in the same information set, and again, the interpretation is player 2 doesn't know what the coin that player 1 got is. And now player 2 has to choose heads or tails, and essentially the payoffs are set in a way that if he's able to match the coin, then he wins, and if he doesn't match the thing on the coin, then he loses. So for example, if the coin is heads, and we're here, and player 2 chooses heads, he gets 1, and player 1 gets -1. Okay? And, okay, the idea is clear, right? Okay, so that's how this game is played. So here's a question for you guys, slightly tricky. In a Nash equilibrium, so we're not being super formal here, but this is a game where it's very clear, I think, what the Nash equilibrium is, or like once you think about it, it's very clear what the Nash equilibrium is. In general, there are some subtleties about defining equilibria in imperfect information games, but here it's pretty clear. So in Nash equilibrium, the question is, what is the expected payoff of player 1? Is it 1/2, 1, 1.5, 2, or 2.5? That's poll number 2. Okay, quite nice. So we have a significant plurality for the right answer, which is 2. I guess some of you have quite a few have chosen 2.5. That could be because of a confusion, but you still understood what equilibrium is. So would somebody like to say what the equilibrium is, and why it's an equilibrium? Yeah.
So it's 2 because player 2 knows that if player 1 bets, then their state is in the left-hand side, so they'll choose tails.
Mm-hmm.
And then if player 1 gets a tails, then it knows that it can fold because its value is going to be higher than whatever it can get.
Yes. Excellent. Remind me your name?
Roger.
Roger, right. So Roger is saying, analyzing the game in exactly the right way, which is, let's maybe take the viewpoint of player 1 again first. So if player 1, if he got tails, then obviously he wants to fold. Anything where he doesn't fold would not be a Nash equilibrium, because this is by far like the highest payoff in the game. Right? So obviously, like if he doesn't fold here, you want to deviate to folding. So if we're in this node, in any Nash equilibrium, player 1 would fold. If we're in this node, it would be crazy for him to fold, because that's the worst possible payoff for him. So if he, anything where he does fold, he would want to deviate to betting. Right? There he can get, the worst he can get is -1. By folding is getting -5. So obviously in any equilibrium, from the point of view of player 1, he would have to fold here and bet here. But then for player 2, basically now he knows that player 1, like Roger was saying, is betting only when he has heads. So now player 2 can play heads, and then when we actually reach the node of player 2, like if he actually has a chance to play, then he will win. So that means that with probability 1/2 we get tails, and then player 1 gets an expected payoff of 2.5. With probability 1/2 he gets heads, and then he gets a payoff of -1. So 2.5 minus 1/2 gives you 2. Matthew.
So what would be done in the situation, or how do you calculate the expected payoff in the situation where the full payoff for tails for player 1 is something like 1/2, so it's less than the maximum of what you can get?
Right. Yeah. So that's what we're going to do until the end of the lecture. Right, but this is sort of a very simple game where we can solve it pretty easily. And it does get, that's why it requires, we won't do it exactly, but it requires more ideas in order to solve that type of game. But the point I want to make here is just like a general point that the simple game is helping me illustrate, which is, so what we were saying is, in this game, we know that player 1 folds here and bets here, and then player 2 can play heads. However, if I change the payoffs, not in the way Matthew was suggesting, but in just flipping this -5 and this 5, then I've reversed the situation. And now, of course, like in these nodes, player 2 wants to play tails, right? So now we have like the opposite reasoning. So the point is that what I want to do in this subgame depends on the payoffs and depends on what player 1 is doing. Okay, so this means that the kind of thing we were doing before, of like doing backward induction from the leaves, that's not going to work anymore. Because what I want to do, even at the level of like the internal nodes above the leaves, what I want to do there depends on a lot of other stuff. Right? So this sort of, I think it's a very nice illustration for why imperfect information is so much more difficult than the perfect information case.
So in this case, how can player 2 be in the left 2 nodes?
So this is just the same situation we had before, where we're saying if, just the reverse. So here, if player 1 got heads, he always folds. If he got tails, he always bets. And then player 2 knows that if we're here, that means player 1 has tails.
Yeah, I know, but I'm saying that here you can't play.
Oh, it can't be in this node.
Yes.
Yeah, sure, that's fine. So remember that when we define a strategy, we have to say what we do in every possible node, including the ones because when we talk about a Nash equilibrium, we might reach these nodes if one player changes his action. Right? So, I mean, when we want to say this is an equilibrium, we have to say, okay, from the point of view of player 1, if we chose to play bet instead of fold, then we know, then player 2 chooses tails here. So you have to say what the other player does in every possible node.
It's just that player 2 will not.
Yeah, sure. So like in this equilibrium, we won't reach that node, but to talk about an equilibrium, it is important to define it for every node. Yeah.
Why is there taking tails back? Because heads would.
Yeah, so he's constrained, like he doesn't know, that's the information set constraint. So he doesn't know if he's here or here. So he's forced to take the same action in both nodes. Okay? Yeah, I mean, there is like, there are two different points here. One is in general, like we have to define an action for every node. But here there's something even more, which is these two nodes happen to be in the same information set, which means whatever action we take in one, by definition, we have to take in the other. Because like player 2 is not allowed to say, I'll choose tails here and heads here. And the reason is that he doesn't know if it's here or there, so he has to choose the same action for both.
So either heads or tails.
Yeah, in both.
Pretty much the same thing.
So if he chose heads, then we would, he would have to choose heads in both, and we wouldn't.
Then the answer would be different.
Yes. Yeah, the answer, his payoff, the payoff for both would be different. But it wouldn't be in equilibrium, he would want to deviate. Given that player 1 is playing this way, player 2 would prefer to play tails in that information set.
Yeah, but he doesn't know what tail or he does.
So in an equilibrium, we're saying, given what the other player is doing, here's what we want to play. Right? So it's sort of like knowing that player 1 plays the strategy. Okay, so again, there is a subtle point here, because what you know in equilibrium is what player 1 plays in every node. You don't know the outcome of the chance node. Right? So for example, you know that in this node, player 1 would bet, and in this node, player 1 would fold, but you don't actually know like in which of these nodes player 1 would end up.
You don't know the result
Of the coin flip, yes. So here, that's our interpretation, right? So what we're saying is in equilibrium, we did this analysis where in equilibrium, player 1 basically has dominant strategies. So he would have to play this way. And then player 2, like we were saying, it wouldn't be an equilibrium for him to play anything else because player 1 is playing that way. But yeah, so in this case, it's sort of a special case, and we can interpret it that way, right?
So in general, you just take the expected payoffs.
Yes, yes. Here we were able to say, like, we know player 2 sort of knows what the coin flip is, given that player 1 is playing rationally, and that's sort of the only thing it can do, like a rational player can play. But again, this is just, that's why I chose this game. It's sort of special in that way. And by the way, I called it a spaceship game because when I drew it out, it ended up looking like a spaceship. Like, this was not intentional. I just drew it, and I was like, oh, this is a spaceship. So it's like in the same tradition of the centipede game. Okay, so again, just to emphasize the point, it's different from perfect information games in the sense that, like, even in these sub-games, like even the small ones, we have to see what happens in the rest of the game to know what the player would want to do. Okay, so what I want to do is talk a bit about Matthew's question of like how we would actually solve these games from an algorithmic viewpoint. So I'm going to focus on zero-sum games. So now we're sort of connecting the two parts of the lecture. The first part was pretty short, but we have a zero-sum extensive form game of imperfect information. And so we said, okay, for zero-sum games we can solve them with linear programming, but if it's a normal form game, but this normal form game is very large. So I want to give you like a more practical method for doing this, or at least the idea of this more practical method. We won't be able to do the details, but just to give you the idea. Okay, so right. So what so the way to think about it is, before we were saying we have this we had this linear program, and we were talking about we had the constraint for what the best response of player 2 is, and then we want to maximize our utility. Now, what I want to focus on here is just the computation of the best response of a player. Okay, so it's a simpler problem. I'm going to fix the strategy of the other player, and I want to compute the best response of player 1 in this case, given that fixed strategy. Okay, so now the constraints. What are the constraints here? So basically, what I'm saying is, if we look at this game, then player 1 has to choose between action A and action B in this node. So he has some probability of playing A, probability of playing B. The sum of these two probabilities is 1. In this node, you can choose between C and D. So we have this constraint, and these nodes are in the same information set. So he has to choose between E and F, and it just has one, it just does it once in a sense. It has to be the same probabilities for both of these nodes. So again, we have the constraint like, PE plus PF equals 1. And of course, all of these probabilities are at least 0. So this is just saying, these are the probabilities of playing each action in each node. Now, like I said, we're going to fix a strategy for player 2. So player 2 just has these two nodes that are in the same information set. So it just has like the probability of playing alpha versus the probability of playing beta. And we're going to fix two probabilities for these, Q alpha and Q beta. And now player 1 is trying to choose the probabilities of his actions to maximize his own payoff. So let's see what we get. We want to maximize over P all of these variables, the following thing. So with probability 1/3 times PA, we end up in this node and get 0. And remember, now we have a zero-sum game, so I'm just writing the payoff to player 1 in the leaves. Okay? So 0 doesn't actually play a role. So let's actually look at the non-zero nodes. One of them is this one. So what's my probability of reaching here? It's going to be 1/3 times PB times Q alpha times PF. And then times 6. So I get 1/3 times 6, which is 2, times PB times Q alpha times PF. Here's another non-zero node. So from this I get 1/3 times PB times Q beta times PF. Okay, so it's like -2 times the product of these variables and constants. And then the other, there are two more non-zero leaves here. This one, so this is 2/3 times PC times Q alpha, and there's this one as well. So we got these 4 terms. So that's my expected utility, and I'm trying to maximize that over all possible values of P. So the problem is that now we're starting to get these products of variables. Right? So for example, we have PB times PF or PB times PF here. And of course, if the tree is larger, we can even get products of more than 2 variables. So some programs with products of only 2 variables are actually convex. This one wouldn't be. But you get into even bigger trouble when you have products of more variables. So this wouldn't work. So what I want to show you is just the insight or the intuition that helps overcome this problem. Okay, and it's really not showing you, like, I'm not planning to show you like the whole solution, but I want to show you the crucial idea that sort of makes this kind of thing tractable and helps us overcome this problem of product of probabilities. So the insight, and it's actually an assumption that we're going to make, but a very, very reasonable assumption, is that the last action taken by a player is the same for all nodes in an information set. And this is called perfect recall. So another way to think about it is the player never forgets something that he knew in the past. This takes a bit of time to digest, so let's talk about it a bit. What do I mean here? So what I want to avoid is maybe a situation like this, where let's say this was like a node of player 1, and he had either the action A or an action B. And then, maybe these were maybe nodes of player 2. And then these are nodes of player 1. So I want to avoid a situation where these two nodes are in the same information set. Right? And I'm saying, like, this doesn't make any sense, because here player 1 chose to take action A that led him to this node ultimately. And player 1 chose to take action B, which ultimately led him to this node. So in order for him to not distinguish between this node and this node, and he took two different actions to get to them, he has to forget that he took the action A versus B. Right? So like he has to forget his own actions in order to not be able to distinguish between these two nodes. So perfect recall says, a player just doesn't forget the actions that he takes, which in particular means that the last action that he took before we reach some information set had to be the same action for all of the nodes in the information set. So for example here, right, so here we took the action B, and then player 2 took some action, and what this says is we can distinguish whether player 2 took the action alpha or took the action beta. So maybe like he's hiding something behind his back or something. So we can distinguish, but at least we can distinguish between these nodes that are in the same information set and this one. Well, okay, this is not a great example, but anyway, you see what I'm saying. Like it's, we remember that the action that player 1 took is the same action in both cases, which is the action B. If we're in some other part of the game tree and player 1 took a different action together, it makes no sense for these different nodes to be in the same information set. Okay, so is this assumption clear? Yeah, Ankush.
Can you define a bit more precisely what an information set is?
Yeah, so information set is a set of nodes belonging to the same player, such that the player is constrained to taking the same action in all of the nodes in that set. Okay, so that's sort of the definition. So in particular, like all of these nodes should have the same action set, and there's a constraint on the strategies that says the player should take the same action in all of these nodes. But again, the intuitive interpretation is nodes where we don't know in which one of them we are, and therefore we can't, when we choose our strategy, we can't distinguish between them. Okay. So any other questions about what perfect recall means? Because I know, like when I first heard it, it took me a bit of time to digest it. I think what's confusing about this is that it's not an assumption about the strategy of a player, it's an assumption about the structure of the game. So basically, the assumption is about which information sets you can have in the game. Right? And it says like you can't have an information set containing nodes that the player reached through different actions. So that's really the confusing part. Yeah,
so is it saying that if we were to instead fix player 1, then that information set that's up there with the player 2, that they'd actually be separate information sets?
Sorry, so you're talking about this game specifically, and you're saying if we fixed his moves like to be the same?
So for this game, we were fixing player 2's moves, or his strategy.
Yeah. Okay.
But if instead we fixed player 1's strategies and tried to figure out player 2's strategies, then the information set, or there'd be two information sets for player 2, right?
So, I mean, the question of who we fix doesn't, I mean, the perfect recall assumption is sort of, this applies to both players. I'm not sure I see your point, but you're saying, so here, for example, like these two nodes are in the same information set. And, but that's sort of fine. I mean, this is just saying like player 2 doesn't know what happened in this chance node. Player 2 didn't actually take any actions before reaching those nodes, so it's fine for I mean, perfect recall is satisfied even for player 2. Okay.
We kind of assume that one player does not see what another player is doing.
Sometimes, yeah.
Like every time. Like in this picture, for example, the second player does not know the first player took the action B or action C.
In this game, yes. Yes.
Doesn't see it.
Right. Right. In this game, exactly. So right. So here, both play. You know, because we have these two information sets, player 2 doesn't know where we got to this node. So like you said, it doesn't know which action player 1 took. But also player 1 doesn't know. Well, it sort of knows that player 1 took either the action C or the action D. I think a better interpretation is it doesn't know what was the outcome of the chance node here. Right. So it knows at least that the player 1 didn't take the action D or A. Otherwise, player 2 wouldn't even be able to play. Okay? But again, you know, there are some extensive form games where each player would know what the other player did. So that, yeah, but this game is sort of like that. Okay, so let me try to give you the intuition of what I'm trying to do here in the last few minutes. So what this thing tells us, you know, when we said player 1 took, you know, we're looking at like PB times PF. So, you know, we took this action, and now we're in this node, and now we're sort of saying, okay, there's some probability that we're in this node, and that probability gets split between two smaller probabilities by multiplying it by PE and PF, whose sum is 1. Okay? But the idea is instead of multiplying it by two probabilities, let's just say I have two probabilities that add up to the bigger probability. Okay? So essentially, like, you know, here, player 1 chose, so basically we got the following situation. So we don't have the product by P, but if we chose B, there would be something where we additionally multiply by P, and something where we additionally multiply by PF. So you can think of this as breaking PB into two smaller parts that add up to PB. By saying, okay, we have PE, we have PF, they sum up to 1, and we take the product. But the idea is, why not instead just say we have two probabilities here, and the probabilities sum up to PB. Okay, so let's see what this looks like. What we'll do is we'll introduce a scaled probability variables P prime X. And the information set constraint is, for all of the nodes in the information set, the sum over P prime X equals to P prime Y, where Y is the last action the player took before we reach this information set. That's sort of the formal way of capturing what I was just saying intuitively. And then to recover the probability, you just take these probabilities and divide them by the probability of the parent. And here the idea is, we said we had this probability PB. So one way to break it up is to multiply it by P and PF. And another one is to say, you know, here's just two probabilities that add up to PB. And to say, what's our probability of taking each action in that node? Let's take each of these two probabilities, divide them by PB to recover those probabilities of taking an action in the node. So what we would get in the game is the following thing. So we have, like before, P prime A plus P prime B equals 1. So far, player 1 hasn't taken any actions. Same for P prime C and P prime D. Same for, and we fix Q alpha and Q beta. So the only difference is now we say, well, P prime E and P plus P prime F equal to P prime B. So that's how we sort of broke down P prime B into these two probabilities. And now this is great, because now we can just say, okay, what's our probability of reaching this node? It's going to be Q alpha times P prime F, which already sort of contains this probability inside it, in a sense. Right, so these are our linear constraints, but now our objective function is also going to be linear, because we sort of care just about the last probability in the path that captures all of the probabilities on the way in it. Right? The probabilities on the way get smaller and smaller, And every time we define these constraints to say the sum of probabilities is at most the probability of the parent. So all of this information is captured in the lowest probability. So now we're able to get a linear objective function subject to linear constraints, which is what we like. It's a linear program. Okay, great. So just very quickly, what we showed, like all of this work, was how to compute a best response for each player. Now we want to use, I want to argue, without showing you the details, that you can still write the minimax strategy problem as a linear program. So you can do it using LP duality. Basically what you want is to embed the best response of one player by using the dual into the problem of the other player. But we won't talk about this at all. The fact is that this does give a polynomial time method for computing optimal strategies. And again, really the takeaway message is the sequence form. It's a pretty simple idea that helps us linearize things and makes this possible. Okay, so just to finish with the story. So this kind of approach, going back to poker. So this was used to compute optimal strategies for Rhode Island Hold'em poker, which is like a simple variant of poker that has roughly 10 to the 8 nodes. This is work done at CMU by Thomas Sandholm and his then PhD student Andrew Gilpin. But heads up, like 2-player, no limit Texas Hold'em poker has 10 to the 167 nodes. So this is a huge, huge game. And so of course it's a much, much bigger challenge. And as you probably know, a few months ago, there was a tournament that happened in Pittsburgh between Liberatus and 4 of the best no-limit, heads-up, Texas Hold'em poker players in the world. And Liberatus won by a statistically significant margin. So this is the scoreboard at the end of the tournament. So parentheses show a negative number. And you can see that all of the 4 players lost by a significant margin, some of them by disastrous margins. Some of them sort of saved face, but still lost. Yeah, so this was, basically they were looking for statistical significance. We're looking at like all of the players together. But actually I talked with Noam, who was the grad student who worked on this, about this. And actually, like even if you removed Jason Liss, who was the worst player, he was also the worst player in the previous tournament. Where the computer lost. But even if you remove him, Liberatus would still win by a statistically significant margin. So this was a very, very decisive victory. Yeah, and so again, like this is why we can move poker in that comic as well to the category of now computers can beat top humans. Cool, that's it for today. See you on Monday.